Hello and welcome to this review lecture for lecture 11 to 13. We will be reviewing the various things which have been covered in these lectures today. So, we basically in this lectures we discussed about the various techniques for realizing physically the ion selective electrodes, and some of the ways which were described were by the use of glass membranes, for example, particularly relevant for the pH measurement application. There are certain glasses which are the chalcogenides, the silicates of chalcogenides, which would be very selective to hydrogen ion over other competing or interfering ions of interest. We also talked about the various crystalline membrane based ion selective electrodes, which would involve crystal membranes like lanthanum fluoride for doing selective detection of fluoride ions and so on and so forth. We also talked about the various natural extracts which are available from trees, etc., which would be in the same manner as happens biologically or naturally, would be able to measure one ion of interest. For example, we discussed about valinomycin, which is a very important organic extract and which is available at the membranes or membranous surface of the cells for doing ion transport of calcium or potassium ions. So, such a naturally available extract can be easily used for a similar application while measuring ion selective electrodes. We described about the various enzyme based membranes which would be selectively able to create a reaction or an influence on a certain target species of interest. So, this is another class of the ion selective electrodes. Having said that, we also talked about the various gas electrodes which are available. The most fundamental measurements that are done are for example detection of ammonia from, let us say, ammonium chloride, and in that light everything converges to the measurement of pH across a glass selective electrode. Following this, we also talked about the various electrodes related to the biological measurements for systems. Herein we discussed things like penicillin sensors, where by using an enzyme called beta lactamase we would be able to change penicillin into penicilloate and a hydrogen ion and essentially measure that hydrogen ion using pH electrodes. We discussed about how to measure glucose again by a change again with an enzyme glucose oxidase of the glucose into gluconic acid and H2O2, which would again effectively result in a increase in the pH of the solution, which could again be measured by a pH electrode. We talked about urea sensor, we talked about various other sensors related to measurements of creatine phosphate, for example, within the human body, or phenylalanine, which is again an alpha amino acid, and it kind of generates information about catecholamines, the presence of catecholamines within the human body, which are hormones released by the adrenal glands in situations of physiological stress, etc., within the body. So, effectively what we saw is that in one way or other the conversion of these analytes have to be made in a manner so that it generates hydrogen ions, which can be measured using a pH electrode. So, at the end of the day, everything measured is in terms of those hydrogen ion releases which have been back calibrated to the concentration of the target ion of interest. We also studied about the electrodes related to carbon dioxide gas sensing or sensing of oxalates, as commonly happens for investigation of kidney stones, etc., where calcium oxalate percentage goes up in particularly urine and so on and so forth. So, we also described the various processes associated with the formation of the interfacial double layer. We theorized about why this double layer comes into existence because of the random motion of some atoms at the interface of a solution and the metal. The random motion is in terms of a sudden release of the atoms into the solution as an ion because of very minute changes of surface energy at the surface of the electrode. The electron cannot escape, as a result of which the electron is always trapped within the electrode, and the atom goes into the solution as an ion, and the moment it goes into the solution, there is a separation done by again a dielectric, a thin dielectric layer of water having a high dielectric constant, which does not let the atom come back and take its position on to its parent electrode from which it got generated. So, this results in the formation of an interfacial double layer, which has a very high electric field owing to the extremely thin nature of the monolayer of water, which is absorbed on the surface by surface energy concentrations. And this potential can go up to a very high level, almost of the level of 1 volt per 10 to the power of minus 9 meters. Okay. So, it is about 10 to the power of 9 volt per meter level. So, that is how high this electric potential can be, and it generally boils down to the fact that all electrochemical measurements have to be in consonance with the presence of this layer, because whenever there is a metal immersed in a solution, this double layer would automatically prop up, and there is a capacitive behavior of this double layer as well as a resistive behavior, and particularly these issues become very prominent when we use high frequency measurements, when the signal is no longer DC in question, and therefore very accurate modeling etc. has to be done associated with this double layer. So, we started theorizing that how this dual layer can be modeled in real systems, and then whatever was associated with the one charge to its environment consideration done earlier in the while evaluating the gamma I or the activity coefficient of the ions of interest. In this particular case, we thought the surface to be composed as if of an array of such charges, and a dual layer being formulated because of an array of such charges, and then we tried to again in a unidirectional x directional manner solve for the potential function, and ultimately the variation along the radial direction in a cylindrical manner starting from the surface of the electrode all the way to infinity was accomplished, which would result in the formulation of the potential at a surface of this electrode very near the start of the dual layer, and we would call this potential the zeta potential associated with such a surface. So, we derived a formulation for the zeta potential at the surface corresponding to a radius r equal to the ion size parameter A, and then we modeled this a bipotential form associated with the electrode as a Helmholtz layer or a Helmholtz potential and the diffuse potential, and we also further assumed that as the electric field percolates into the space filled with the dielectric fluid, and as it goes beyond the Helmholtz layer, there is a rapid depreciation of the electric field as a square of the inversely as a square of the distance from the particular surface, and therefore a potential plot if made would surmise to the linear drop of the potential across this Helmholtz layer, following which almost exponential 1 by r square drop 1 by r drop of the potential across the diffuse layer. And so, therefore, the diffuse layer would be self thinning in nature, it would automatically thin out with the distance as a function of r from the start of the diffuse layer onwards as you move into the solution, and basically it would again come down to 0 theoretically at a very large value of radius equal to almost infinite distance, although it would actually come down to a realizably small or negligible value at a much earlier point of time. So, what we essentially now looked at was a capacitor model with a Helmholtz capacitance and a diffuse capacitance, and tried to model a surface based on a parallel combination or a series combination of these two different capacitances as across two potential points. So, from this there emerged a very interesting concept and theory that what happens, for example, in a microchannel when the surface would be charged and develop a zeta potential in contact with a fluid of a certain pH, and we try to now look at the different flows of interest varying from the simple covert flow across a single flat plate as the fluid would move against the flat plate to a model where this fluid would move between two flat plates, which would essentially result in the generation of the parabolic flow profile, and we derive for the velocity using the Navier-Stokes conservation of momentum equations under certain boundary conditions, and found out what is the variation of the velocity from the axial center of such a combination of twin plates, okay, all the way to the static layer or the immobile layer of the fluid, which is more towards the surface. So, once we generated that, we tried to estimate in a similar manner what would happen when there is a formulation of a zeta potential in addition to a simple pressure driven flow case, and there we sort of tried to model that what kind of force would be needed to separate this dual layer, so that the charges in the diffuse layer would move perpendicular in a direction perpendicular to the direction of the field as associated by this dual layer and diffuse layer. And we found out that there is a condition corresponding to a situation when the electric field would give enough force, so that the layer would separate across the dual layer and move as a plug. Okay. And so, we tried to derive what would be an ideal velocity or a velocity or what would be an ideal force or a velocity in such a situation where shear would happen exactly at the dual layer interface. And this phenomena is also known as the electro-osmotic flow. So, we talked about how this flow would be influencing, let us say, a silica surface which has been charged to its point of zero charge, and then taken slightly above the point of zero charge, maybe to the negative pH, or maybe slightly below the point of zero charge to the positive pH, and then associated dual layer which would be formulated, how it would move. We tried to find that out using electrokinetic theory, and essentially that would result into the mobility equation, where as a function of electric field you can equate how much the ions would be mobile for a unit field, and multiply that with the electric field to find the overall velocity of the ions in question. So, this was in a nutshell what we tried to do for estimating the electroosmotic velocity, and then we applied these further for designing the electrokinetic network of flows, particularly for a case where there would be a crisscross based channel like this which is present, and then we would try to apply potentials at different endpoints of this crisscross, and would deterministically find out what is the mobility of an ion, and with a certain field what would be the velocity of flow, the flow discharge of such a system. So, we designed this electrokinetic network of flow, and here we used the simple network theory for predicting what is the current associated between unequal potential points on two sides if exists on such a network, and this way we realized a very strong design of the electroosmotic pump. Okay. We also talked about several other electrokinetic phenomena which emerges from what is the cause and what is the effect. For example, in the electroosmotic flow, the cause really is the electric field, which is the driving factor, and the effect is really the velocity which gets formulated of the charges because of this electric field. Okay. So, there are several other associated phenomena which are also grouped under the domain of electrokinetic phenomena, where in one case, just as the electroosmosis case, if you consider motion caused by EMF, the other important phenomena associated with such a motion would be the electrophoresis. Okay. So, in electroosmosis, the whole dual layer moves as a plug, but in electrophoresis it is the movement of a single ion, probably to the opposite direction, in a applied field of interest. So, again the motion is the cause and the effect is the electric field. There is also a reverse way out of looking at electrokinetic phenomena, that if you cause motion, it may change or it may result in a potential coming out because of the motion. For example, we discussed the phenomena of streaming potential, where a potential would be produced by a liquid being forced through a diaphragm through a set of micro capillaries, and one of the reasons why that would be so is that you are disturbing the electrical double layer by physically applying pressure to make a shear action possible between the electrical double layer, which would force this layer to move against each other. So, there would be the tendency or generation of a electric potential because of that motion. So, we also talked about sedimentation potential, which is used more from a chemical industry concept, where because of gravity action whatever particles come into motion in a stream of flow of fluids would generally result in some kind of a potential associated with that kind of a flow. So, as the particle is falling because of gravity through the fluid, there is always a increase in the potential or the charge on the particle because of such a flow. There again the cause is the motion and the effect is the potential. So, it is the reverse. So, we discussed all these electrokinetic phenomena from a standpoint of their models, estimated the various parameters like velocity, pressure of flow, the surface charge density which would happen, and also estimated the zeta potential in terms of several of these phenomena, several of these parameters which would otherwise be experimentally determined, and finally arrived at a way of defining or determining the zeta potential associated with the surface. So, this in a nutshell is what we covered in lecture 11 to 14, and we would again follow another review session for the later on lectures. Thank you.